Okay, so looks like we're live, and this is just kind of an update video that I've been trying to push on my YouTube channel. This is just a test video. I think I'll do better and more streams. I mean, full-fledged 2 or 3 hour long streams. But this is just a test video, test if everything is working right on my computer or not, and then we'll go on. Okay, then we'll go ahead. So but I still have to record something, right? I can't just leave the subject blank. Otherwise, just like an email, it will go into spam, and then the other person will have to, I mean, search it through their spam and look for it, and it might take them even 3 to 4 weeks. So it's waste. So I will really do something. I have to do something. So let me just show you guys what I have been working on recently. So let us open Emacs, GitHub, H1, and yes, this is, let's open pyhash.h. Yes, and okay, so let's see. So this is what I've been working on. Okay, if you can't see it, let me zoom it. This looks much better. So this is what I have been working on. So the first line itself is basically what it actually does. Okay, so it's a header file for function related to AH1. Now it has been named to pyhash. It has been renamed to pyhash, but it was earlier AH1. And I've been working on my own hashing algorithm. Okay, so for those who don't know, let me explain it. What a hashing algorithm is. So hashing algorithm is basically a one-way function. What is a one-way function? Let me show. And control x3, yeah, here we go. And let me also open the C file. Yes, so this is the implementation, and this is the public header file, which if one of you guys want to use, you can. And it's live on GitHub, so you can just copy paste the source code, no problem. So this is the implementation, and let me just show you guys how it works. Okay, Windows, let's go to SPH1, and yes, we have here, I think we have a REPL. Let me remake REPL. Static. Okay, and we get an unused function error, so I should probably comment it out. Where is mix 32? I think it's below. Yeah, I got it. Mix 8 and mix 16 are unused. Yes, they are. I know that. So let's just comment it out, and let's go to here, and let's compile it. Make REPL. Yep. So the source is the compilation is. So actually, let me clear it. So what is a one-way function? Let me just enter any text. Okay, any text. Let me just type hello. So we get these weird numbers, right? What are these weird numbers? So these are numbers which can be used to identify, or maybe I think a better word is verify, that what the contents of this text is. And how is it a one-way function? If you know that the message I typed is hello, you can convert from hello to these three numbers. But if you want to convert back from these one of these three numbers to hello, that's practically impossible as of now. Okay, quantum computers might change it, but with conventional computers, not really possible. And these are unique to any series, any sequence of bytes you give it. By byte, I mean the literal computer byte 01. Okay, so let me just do word. Okay, so the numbers have changed, and you cannot retrieve from any of these numbers this. And these are numbers. Okay, these are hexadecimal numbers, so we have F and E for everything, right? And I can actually enter anything. And let me just do this. In fact, if I change, let's say, just instead of HELLO, let me make it HELLP. Can you spot the difference? The whole numbers have completely changed. And this is the beauty of hashing algorithms. You literally cannot retrieve from these numbers these input texts. Okay. Now there are already very good hashing algorithms out there for non-cryptographic purposes. We have city hash, we have XSXX hash, we have murmur hash, and we have for cryptographic reason purposes we have SHA, and earlier we had MD5. Is MD5 actually a cryptographic hashing algorithm? I'm not sure. I'm not really sure, but this is what I've been working on. Okay, and if you want to see the implementation, let me show you guys. Um, so what we first do is in the implementation, actually I should show you the header part. Okay, so there are three functions: pyash32, this is the 32 one, 32-bit number, it will generate 32-bit number. We have a 64-bit number, we have a 128-bit number, and I had a 256-bit function which I want to deprecate in version 2.0, because this was intended for, I mean, hashing for this is intended for use in hash tables, not really large projects. Okay, for any serious project that even I am going to do in future. Um, as of now, I'm very much interested in the implementation of XX hash because they have SIMD instructions, and I want to do SIMD instructions in this, but I don't think it's even required because, come on, you do not need to overcomplicate things that can just be very simple, right? Especially in computer science, it's a pain. And for each function, we have implementation of it. So let's go to first, let's first check pyhash. Let's check pyhash 64. So what do we do here? Param bytes. Okay, so we take bytes, take a series of bytes, and they're restricted because we are not going to manipulate, change them. There's const, makes it constant. Restrict is a special keyword that I think you should use. It is very good for compiler optimizations, and I think libc uses it a lot. In fact, if I go to man printf, man3 printf, right? Printf. Yes, so you can see here, even printf uses restrict because it's not going to change the string you pass it, right? And we have, and what we do is first we have some initializers for registers. So you don't really generate a 64-bit or 128-bit hash directly. So you have multiple registers. This one has 4, MD5 also has 4, and what we do is that we initialize them with some variables. We then in this part we basically capture the tail of the bytes. Okay, so we are actually, the program actually reads in chunks of 16 bytes. Okay, so 16 bytes, and what we do is in the first part we read the tail. So let's say that our input data is 20 bytes. It's not a multiple of 16. So if we are only reading in multiples of 16, we will read till 16 bytes, but then the extra 4 bytes are left. And this can be a disadvantage because you can get a lot of hash collisions, right? Which for data which are not multiples of 16. So this is where this part shines. And what we do is we first read the tail, and that takes the last 16 bytes. So there is some overlap, but that is not really a big issue. And we read it, and then this is a series of chains. Not chaining is done in the next step, but this is actually, we do chaining here too, but this is a series of mixing the values. Okay, so we rotate it, and this is basically the shift rotation. Okay, like if you have 110 and you right rotate it by 1, then it becomes 011. Okay, if you have ABCD and you rotate it, then it becomes DABC. If you rotate it by 1, if you rotate it by 2, it becomes CDAB, right? So we are doing the same with, but with bit, at a bit level we are doing this. Do this with tail and we read 4 bytes more, and then 8 bytes we read 8 bytes more, then 12, and the last one reads the all the 16 bytes. Okay, we multiply it with a big number so that it, and it's actually a prime number, so they are very carefully chosen numbers. Okay, so they are prime numbers, and you actually test them against a lot of numbers, and the best ones which perform stay, so that we get the maximum mixing. And there is something called Hamming distance score. So you actually try to maximize, not maximize, you try to make the Hamming distance score to get the Hamming distance score to 50%, so that every bit change, even the smallest bit change, causes a 50% avalanche. So basically, even a small bit change causes 50% of the bits to rearrange or flip. Then we add here W, which is the previous register's value, so that we form a chain, so that the first basically 4 bytes affect the next 4 bytes, and we repeat this for the other registers too. And the same thing is repeated for the 16-byte chunks which we read. You can see here for when we loop in 16 bytes, and then we move the byte pointer by 16 bytes, and then we loop again. And here I have stolen this part directly from city hash, and almost everything else is my own implementation. Okay, and it's actually working very nice till now. In fact, I'm so confident I can test it. Make test. Please compile. Yes, it's compiling. And you can see, I won't run all the tests here. It will take around 15 minutes in my computer. So we just did a collision test for this file, top 10,000 Googled words. Okay, and for 10,000 words it has found 0 collisions for 64-bit hash and 0 collisions for 128-bit hash. Even for dictionary sets as large as 1 million, I have tested it, it's 0. So I think it's a good enough implementation for something I have been doing for fun. And you can even see the Hamming score for the 32-bit mix function is around 50%. Okay, it's actually very less deviation from exactly 50%, so it's fine. It's already on GitHub, so you guys can check it out. And the next project I'm working on is about to come soon, and it's going to use SDL3, and I have used SDL2, but I have not used SDL3. So my plan is to learn the newer version of SDL through that project. So that's it for today. I'll see you guys again in my upcoming stream, hopefully. Let's hope so. I mean, I have a lot of exams also, but I think we can make it possible. Yeah, so bye.